Your job here at companies like this is really important to prevent bots and malicious actors from creating accounts and making posts. So to solve this problem, we want you to train a machine learning model that can flag accounts as potential bots, which then go to manual review. Hi everyone, we're here today with Nathan for another machine learning mock interview. For those of you who aren't already familiar with Exponent, Exponent helps you get your dream tech career with our online courses, expert coaching, peer-to-peer mock interviewing platform, and interview question database. Check it out at tryexponent.com. Okay, thank you so much for being here with us today, Nathan. Can you introduce yourself quickly for our viewers?
Yeah, hi. So my name's Nathan. I'm a fifth-year machine learning PhD student at the University of Toronto and MIT, and I'm really excited to be doing this interview today.
Awesome. Okay, I'm really excited to hear all about the expertise that you have to offer us today. So let's get right into the question. So the question today is, suppose that you work at a social network tech company, and your job here at companies like this is really important to prevent bots and malicious actors from creating accounts and making posts. So to solve this problem, we want you to train a machine learning model that can flag accounts as potential bots, which then go to manual review. Since bots are more rare than real humans, our initial training dataset consists of a set of account metadata, where a majority of the dataset is actually comprised of humans. So considering that you have this deep class imbalance in the data, what considerations would you make when you're trying to select a model and training it on the data?
Yeah, I guess my first question here would be how bad is the imbalance? Like what is the proportion of the data set here that is bots versus humans, given that it's a binary classification task?
Yeah, that's a good question. So would you handle it differently if you had 30% bots versus 5% bots?
Yeah, so I think with 30%, that's kind of within the range where we might expect the class imbalance to be not as much of an issue, and we can kind of go ahead with our standard training pipeline of training our model and evaluating just as we might normally do. But with 5%, it becomes a lot more difficult to kind of train a model, especially if our training objective is something like ERM, where the model can kind of find a naive solution simply by just predicting that everybody is a user, and it gets really strong, what looks like really strong performance because the accuracy would just be 95%, and we get lost on the examples that are bots. And so for 30%, I think this is something where I would keep in mind that there is a little bit of an imbalance in this task, and maybe make sure to monitor some metrics during my training. But for 5%, I think I would need to take a little bit more of a thought process into my data pre-processing, and as well as the kind of algorithms that I'd be selecting to train a model with.
Right. Okay. Can you quickly explain what ERM is?
Yeah. So ERM stands for empirical risk minimization, meaning that we're minimizing the risk, meaning whatever loss or cost function we choose to optimize over the empirical distribution that we sample from that we achieve from looking at our data set. And so given that our empirical distribution here is going to be our class distribution empirically is 5% bots, this means that a model that's trying to achieve the best empirical risk might try to optimize only on predicting the users correctly and kind of fail at predicting the bots, which is kind of the reason that we're training the model in the first place.
Right. Okay. So under ERM, then, as you mentioned, if a model just predicted that every single data point came from a human rather than a bot, it would actually still do pretty well, and that's not what we want, right?
Right. And I think one of the bits here is that it, at least to somebody who doesn't realize that there's a class imbalance, it looks like it does very well. And there's a few other metrics that we can look at to kind of evaluate whether or not it's actually doing well, and gives us a better picture than just looking at the log likelihood loss or looking at the accuracy.
Cool. So let's say then that we're continuing forward with the assumption that 5% of the bot accounts are actually bots. So then how would you handle that kind of data set?
Right. So I think there's two kind of orthogonal approaches here that are kind of complementary, and you can use one or the other or combine them both. I think the simplest one, and this depends a lot on the dataset size, is going to be either dataset class subsampling or oversampling. And so I think like what size is the dataset here that we're dealing with?
Mm-hmm. Well, how would you handle it for different data set sizes? Like, let's say it's like a smaller data set versus a large data set. Like, would you change your approach?
Yeah, so with a smaller data set, so when I talk about data subsampling, what I mean is that we're going to remove a lot of the majority class examples. So we're going to kind of subsample the human examples. And so we can achieve a closer to 50-50 or even 60-40 distribution of humans to bots in our data set. And so if we have a lot of data, then this means that we can still get a good distribution of examples between the two classes, while making sure that we have enough examples that our model actually learns a good classifier. But if we have very little data, then by subsampling our examples, we'll have a very small data set. And so we might imagine that our model is going to learn a much poorer classifier. If we have a very small amount of data, then we might want to think about something like oversampling, where we take the examples that we have in the majority or the minority class for the bot and simply repeat them multiple times in our data set, or even do some intelligent batching strategy if we're training something like a neural, where we try to make sure that the seeing some minority class examples in every batch that it's being given to train on. I think another approach, if we don't treat our data set as fixed, is that we might want to go out and acquire more kind of minority class examples. So going out and trying to specifically find more bot accounts that we can get examples for that we can put into our data set. And this might be kind of cheaper in the long run than trying to oversample or subsample and getting maybe a weaker model versus just trying to get more data overall to help alleviate the problem.
Yeah, I like that you mentioned the idea of also gathering more data rather than simply like upsampling or downsampling some of the data. Because what's potentially some issues that you could run into if you were trying to, let's say, upsample the minority class, which in our case is the bot
right
data.
So a few issues can happen if we're trying to upsample. One of them is that the bot, or not the bot, the model learns kind of to associate spurious correlations with the bot class. If a lot of our bots are coming from one specific place, maybe a majority of the examples come from one place, and we kind of oversample these specific examples in our data set, then the model might learn to associate accounts from this area with being bots rather than learning kind of the true information or the true relationship between kind of the metadata features that we're given and the class, whether they're a real user or a bot. And so if with a small amount of data, since we're given kind of a very small sample of examples from the minority class, these kind of spurious correlations, if they exist, can kind of become much worse as we oversample the data.
Okay, great. Those are great examples. Okay, so now that we've thought thoroughly about how to collect this data set and either like augment or upsample or downsample, now we have to actually approach the modeling problem itself. So how would you start out with the algorithmic approach? Like, how would you come up with a learning objective and how would you select an appropriate model?
Right. So I mean, broadly speaking, I think this is just like a binary classification problem. And so kind of any binary classification model would work here. I think as a starting point, generally I would start with the most basic kind of a model. So this is something like a logistic regression model, a binary decision tree. And so with a decision tree, we can kind of and even with a classifier trained on say log likelihood for a logistic regressor, one of the ways that we can take an algorithmic approach to fix the issues of class imbalance are that we can give specific weights to the loss functions that we're using to optimize our models. So for example, with logistic regression, if we're using something like binary cross entropy, we can penalize the loss on the minority class much more than we might for the majority class, and say, if you get this one wrong, then this is really bad, versus saying that if we get a majority versus a minority class wrong, they're the same weight.
Okay. Yeah, that makes a lot of sense. I like that you discussed like multiple different approaches and like the trade-offs of the models, you know? Okay. So we talked a little bit about like both a binary, both a decision tree and a logistic regression. And you mentioned that like one might be more interpretable and one like can actually give you like a probability at the end, right? What might some other trade-offs of selecting these different models be?
Right. So with a decision tree, as you mentioned, we get a little bit of we get something interpretable where
Yep.
we can kind of trace through the model and say, you know, why is it making the decision that it's making? But of course, with this kind of decision tree, it's not inherently probabilistic because we're kind of given a single binary decision whether you know, an account is a bot or a user, and so with a probabilistic approach, this allows us to do different kinds of things like thresholding our decision, kind of changing the way the model trades off between you know, how probable a user might be to be a bot or not. It also allows us to perhaps take a Bayesian approach here. So if we have a prior probability based on kind of the empirical class distribution that we believe that, you know, in general, a user is much more likely to be an account is much more likely to be a user than a bot. Then we can take this into account when we kind of update our beliefs about an account being you know, a bot or not. And so even if the model predicts, you know, a very high probability, we might not update our prior as much. And this also allows us to say ensemble different models. So we have one model that is able to you know, perform really well on a certain kind of account to predict bots, and another model that predicts bots well on another kind of account. We can combine both of these models together using you know, a Bayesian posterior by incorporating both of these new information beliefs and potentially weighting them differently into making a final decision in our model.
Okay. Yeah, that makes a lot of sense. I like that you mentioned the model ensembling approach. So you don't necessarily have to choose one model or the other. You can actually use both, right? So you mentioned that in order to do this, you actually have to select weights for each of those models. How would you go about selecting those weights?
It's so kind of the simplest approach here would be simply to use the kind of empirical distribution. Ideally, we'd like to weight somehow by the true probability distribution of a user being a bot or a true human. But of course, we only have the dataset statistics to go by,
Oh,
and so if say
oh, I meant like,
the 5%,
oh,
sorry,
oh, I meant like, how would you weight each of the models? If you're doing a model ensemble and like, let's say you want to like weight each of the model predictions,
I
how
see,
would you decide what those weights are?
right. I think it depends. One simple method is simply to take a validation set and fine tune a weighting scheme between your models to achieve whatever highest metric you'd like on the validation set.
Yep.
Other kinds of methods might be to think about some kind of routing mechanism. So we might be routing certain kinds of accounts to one model. Like in my past example, you know, we might have one account. You know, accounts in a certain region might exhibit different behavior from accounts in another region, and so we might imagine that rather than a bunch of models to predict you know, the behavior overall, we might train one model for a region and then kind of route an account that's been flagged to be evaluated into the region specific model. And so there's to kind of do this ensembling approach. I think it depends on kind of how much data we have and especially on the kind of features that we have. One kind of downside of having this region specific approach is that a model that learns from all of the data kind of has access to a lot more of the relationships between the other features that we might be interested in.
Yeah, yeah, that makes sense. It's a drawback because then you have a smaller data set to train on per like region specific model, right? But on the other hand, ensembling models in general can lead to more robust performance, right? So it's always a trade-off between the two approaches. So
Right.
I know you mentioned in order to determine what the weights should be, you would use a validation split of the data. So can you tell me a little bit more about how you would split your data and what general heuristics are you using for to determine like how much of the data should go in each split?
So in general, for training any kind of model, we want some kind of training validation test split, especially when we might have a lot of potential hyperparameters to tune, like say the class weighting scheme or the ensembling weighting scheme as well. And so we split our data into a training set which we use to train all our models, and then we tune our hyperparameters on our validation set, and then we finally report our results on the test set, which we believe should be representative of how our model will perform in the wild. Of course, this is usually we would do something like a 90%, 5%, 5% split. But depending on the data set size and class imbalance, this makes it a little bit difficult because with so few kind of minority class examples, we want to have as many of these to train on as we can, right? Any example that we put into a validation or test split is an example that the model doesn't get to see and doesn't get to learn from. And so I think it would honestly depend on the data set size. I think I would want, on the order of 500 to 1,000 examples for a validation and test split. And so, if we had 100,000 examples, then maybe I would do something like 96 and 2 and 2. Whereas if we have very few examples, I might do, I might even kind of look at the examples and even kind of manually try to arrange them into a training, validation, and test split, just because if we assign them randomly and don't check, there's a small probability, but not a zero probability that some of these splits get very few of the minority class. And so there's a little bit of checking that needs to be done here to make sure that we're getting kind of as much information into the training set as possible while ensuring that we're getting a good signal from our validation and test sets.
Gotcha. Okay, so in order to get more signal into like the test and validation data sets, we have to consider carefully the fact that the bot accounts actually form this deep minority of the data, right? So do you have any methods for possibly rearranging the splits a little bit to make sure that those bot accounts are captured appropriately in each split?
Right. So one method that I can think of as a kind of basic approach is to do some kind of k-means clustering. And so we might imagine selecting some reasonable amount of clusters, say 10 to 20, and performing some kind of clustering approach on the existing kind of bot accounts. Since just going back to my region examples, maybe we have a different set of accounts from different kinds of regions, and so a random split could potentially place a large percentage of the training examples might just randomly be from a certain region and might bias the model to learn correlations from this specific class of examples. And so one thing we can do is try to do a simple k-means clustering, and then from these clusterings we can do stratified sampling by performing the training, validation, test split of our kind of minority class examples, specifically on the clusters that we've learned from our k-means model.
So you're clustering the data overall, not specifically within each class?
Right. Well, I would apply this specifically for the minority class. I think it's maybe less important for the majority class because we have so much data.
Yeah.
Just in case there's some kind of basic correlation that we're missing out on, and we want to make sure that we're getting kind of an equal proportion from each of the potential subclasses or clusters that we might have in our data. And this should give us kind of a starting line for where we might imagine doing a bit more data set filtering or splitting.
Yeah, I like that. I think it makes sense to think about how there might be subclasses within the bot data as well. And so speaking of, is there any way that you can try to detect whether or not, or can you think of any possible sources here of train test data leakage?
Yeah, I think there could be, right? So if we're talking about account information, it's possible that somebody could have created two accounts or maybe similar accounts, and maybe one was flagged as a human and maybe one was flagged as a bot, or just based on the way that the data was aggregated or the data was pulled to generate the data set. we might have a lot of duplicate, examples. And just as I don't know if you're talking specifically about kind of the data deduplication or pre-processing in the class imbalance step, but a general step would just be to kind of look through the data and to see whether or not there are any immediate kind of looking at, say, the account creation date, say, and seeing if there's any duplicates on.
Yeah, okay. That makes a lot of sense. Yeah, and you can also imagine that you might not just have data duplicates, but you might also have, like with bot accounts, it's very common for like a single person to have created like a large number of bot accounts with like a single script, for example, right? So those bot accounts might all look very similar, even though they might not be the same. And so if you have very similar bot accounts that occur both in your training data and your test data, that could be considered a form of leakage because those are all basically coming from the same source.
Right. And so I think this is why kind of a simple clustering-based approach might be able to find these relationships. As you mentioned, like if all the accounts were created at a similar time, we want to perform stratified sampling to make sure that we're observing a similar distribution within the minority class for each of our splits.
So we've talked a lot about the data now, and let's say you now have this like really beautiful, well-balanced, clean, no leakage data set. Okay, so, and you also have this model too, this model that we talked about, the ensemble model. We've thought really carefully about it, and now we've trained the model on this data set. So lastly, how do you actually evaluate this model?
Right, so I think for any kind of classification task, I think the most immediate answer would be just accuracy. So what percentage do we classify correctly? But as I mentioned before, when we're training a lot of these models, accuracy doesn't really give us a picture, because a naive classifier would get 95% accuracy if it just predicts that everybody is a user. And so there's a few other metrics that we might want to use, and a lot of these hinge on looking at the confusion matrix of the true and false positive rate and the true and false rate. So like the true positive rate here is simply the rate at which our model is able to predict, of the predictions that it makes, how many are true positives. So how many are actually in the correct class. And so we can look at two metrics here, one of which is precision. So precision here measures how many of the examples that we flagged as bots were actually bots. So how precise are our predictions. And we can also look at recall. So what is the proportion of total positive examples that we're actually classifying correctly? And of course, there's inherent trade-offs here. So for a kind of bot, a bot classification task, we care about the false positive rates, because a false positive means that we're flagging an account as a bot that's not actually a bot, and so that means that somebody will waste their time analyzing an account that's not actually a bot. Whereas a false negative means that a bot doesn't get flagged and gets to continue on with what it's been doing. And so in this case, I would say that potentially, a false positive is maybe more amenable. It incurs less marginal cost than a false negative. And so we might want some kind of metric that accounts for these kinds of things. Two of them that I can think of immediately are F1 score. So F1 score is simply the harmonic mean of the precision and recall, and gives a good sense of kind of how we might think about the classification performance, taking into account the class imbalance here. There's a couple strategies for doing F1 score, thinking about individual classes as well. The other most common metric, I think, is AUROC. So this is the area under the receiver operating characteristic curve. So the curve measures the trade-offs between your true positive rate and your false positive rate as you change your threshold, applicable to kind of models that generate some kind of probability distribution rather than a simple binary classification. Of course, when we think about, say a decision tree, here we can only use F1 score because there's not really a threshold that we can think about trading off between true positives and false positives. And so this is another kind of downside of using kind of binary decision models rather than ones that output a probability distribution, is that we're able to kind of control the trade-offs between the costs of a true positive and a false positive.
Okay, perfect. And for clarification, this is all assuming that the manual review that the model's predictions go to afterwards is basically gold, right? Like it's ground truth, like assuming the manual raters don't really get it wrong.
Right. And I think it's possible that we might even try to incorporate some bot level into our training task. So maybe we might classify a bot that's trying to influence an election as a very high level bot that we would want to flag and kind of make sure that we always kind of do manual review on and investigate very carefully. Whereas a bot that's kind of sitting around and maybe liking posts isn't as important to kind of flag, and we don't necessarily need a really strong model on here. And so this kind of stratification of severity of bots is another thing that we might use to kind of improve the classification and granularity of our models. And all of these can kind of be incorporated into our metrics as well. For example, we can measure the F1 or AUROC for a specific severity or class of bots that we would want to classify.
Yeah. Okay, great. I like that. And that provides more information to downstream to the human raters too, to help them make more informed decisions about whether these accounts are actually bots or not, right? Yeah.
Right.
Okay. So then another question I have is like all of the metrics we've discussed so far have been kind of accuracy based because precision and recall are still looking at whether or not the predicted label matches the expected label, right? Are there any other things that we might want to evaluate the model on that aren't strictly about accuracy? So for example, one thing that could be really costly with a model like this is, let's say the model classifies an account as a bot, it gets to the human rater, but the human rater makes a mistake and decides, okay, we're going to shut down this account. But it actually belongs to a human. And so there's a lot of cost there. And so this could have a negative impact on humans, but different groups of humans might be treated differently by this model. Is there some way that we might be able to evaluate that?
Oh, I see. Yeah, you can do some kind of group specific models or metrics that look at group performance. So these are more along the lines of fairness. And so, for example, if going back to this region example, if the model learns that there's a higher probability, it associates a certain region with bot accounts, then we might expect there to be a larger false positive rate for human accounts in this region, and so we might want to look at the kind of fairness across groups and ensure that we're achieving similar metrics within each class, within each group, for different kinds of protected attributes across all of these similar metrics.
Yeah, that could let you calculate sort of like a bias score, right? Something like the difference in accuracy between those different groups. And that's also important to look at too. Okay, and this is one last thing that's sort of related is, okay, so what happens if, like, let's say one of the groups that is producing these bot accounts has become wise to the fact that now you can very accurately detect their bot accounts. And they've made their algorithms more sophisticated so that they can come up with these bot accounts that now look very different from how the bot accounts used to look. How would you go about detecting that? And how would you also resolve it?
Right. So this is a form of kind of distribution shift where we've trained our model on a certain set of data, and it's learned some certain attributes or patterns in the data. But now the bots that are coming out potentially may exhibit some errant behavior that's not picked up on by our model. And so I think one way we can kind of measure the distribution shift over time is to ensure that we're doing regular evaluations of our model on kind of a gold standard set of bots that we want to classify correctly, and ones that are kind of at the highest risk. And so we might imagine setting up some kind of pipeline where every month or two we take the bots that have been evaluated so far, whether they're actually bots or actually humans, and we basically test the model and say, how is it doing on all of our different kind of metrics that we look at, maybe group fairness, AUROC, F1. And, if the distributing over time, we might observe that, as the the bot account creators, get wise to our tactics, then our metrics decrease. And so when our metrics decrease, there's a few things that we can kind of do. One of them is simply to retrain the model. So gather a new set of data, hopefully kind of figure out what is going on, and retrain our model to specifically kind of counteract the new bots that are being created. We might also imagine, if we have something like a neural network, maybe most of our model is correct, and all we need to do is fine tune. And this would be relevant if we have kind of a very large data set and a very large model that we don't want to spend time retraining from scratch. And so we might fine tune, perhaps even specifically on the kind of problem bots that are giving our model a lot of issues, right? This kind of links back to a lot of work on there's a lot of information on adversarial examples where maybe the bot account creators are figuring out exactly what does and doesn't get flagged. And so there's a lot of kind of strategies around trying to make sure our model is both adversarially and distributionally robust to ensure that it works well over time. But this is all kind of contingent on ensuring that we have a very robust evaluation pipeline and really good evaluation metrics that allow us to monitor the performance of our model over time.
Yeah, and this also relies upon you having really good labeled data, right? So in order to detect that data set shift in the first place, that means you need to have some source of bot, like some way of labeling those bot accounts that doesn't depend on the model, because the model might get it wrong. So how would you go about getting that data?
Right. So of course the gold standard here would be to just do a very full investigation into each bot and have a human or a panel of humans decide whether or not somebody is a bot. One kind of approach that might work to automate this approach would be to say take two different models and do a kind of expectation minimization problem where we take the examples that one model classified correctly but the other model did not, and the examples where the other model classified correctly but the first model didn't, and use these examples specifically to train the model to kind of cover up the deficiencies that it has. But of course, this all kind of relies on having really strong gold labels, which a human may or may not be the best person to do so. And so for this kind of approach, we might initially focus on kind of the worst severity of bots, right? So whether the kind of basic level bots that aren't really producing much malicious content are distributionally shifting over time doesn't necessarily matter as much as the ones that are, say, creating a lot of harm on our platform. And so one of the ways we can try to decrease the marginal cost of getting these gold standard labels is to make sure that we're focusing kind of only on the most severe and most severe actors, as well as kind of focusing on the examples that the models get the worst performance on, the ones that it's most kind of bad at predicting.
Yeah, okay. So I like how this is almost like an online feedback loop where you basically constantly monitor the data and also how the model does on that data. And that's so important in general for machine learning model deployment. Mm-hmm. All right, Nathan, you did a fantastic job today. Thank you so much for teaching us all about how you would approach this problem. I'd love to get into a little bit of evaluation of this interview. So can you tell me a little bit, like, how do you think that went? What do you think went well? And what do you think you would change about it?
I think it went fine. Maybe, not, like the most amazing interview I've ever given. But I think I covered most of the points that I wanted to cover. And, whenever a decision came up to be made, whether to pick a certain, objective function or pick a certain model, I thought it was good to mention a lot of the pros and cons that come with each one. I think that there's a lot of nuances that I maybe didn't touch upon. And so one of the ones that ended up coming up kind of over time was this notion of group fairness, as well as kind of, subgroups within our minority class. And so I think a little bit of time could have been spent in the beginning, kind of prodding a little bit about the nuances of the problem and thinking about, what is the scale of the data, what kind of areas are these, bad actors and bots coming from, what kind of meta information. We never looked at, we never discussed kind of what features we have. And so one of the kind of things that we might even do with this kind of online, adversarial training where we'd like to kind of keep up to date with the distributional shift is we might try to acquire new features, right? And try to get more information and more signals that allow us to make a better model.
Yeah, those are all really great points. And I agree with a lot of them, actually. I thought that you did a really good job of balancing between talking about like your machine learning expertise and like incorporating those concepts, but then also bringing in some of like the product sense and also looking at like the real world scenario, right? Because the machine learning can't be used in isolation. We have to consider like the actual use case, and there's always a lot of trade-offs. So you mentioned a lot of really important trade-offs, like it's often helpful to have a model ensemble, but if the models are specialized, then that means that maybe there's going to be less data used for training one of the models. And you also talked about some of the trade-offs of like undersampling versus oversampling data and so on. And yeah, as you mentioned, there was like a lot of different nuances or like details of the problem that you could have considered. So one thing that maybe we could have talked about a little bit more about was in the evaluation setting, you did touch a little bit on like the group fairness. Something else we might have also talked about is maybe the sensitivity or the robustness of the model. So that's a sense of how much does the model's predictions change depending upon how much the input changes. And this is also very related, I think, to adversarial robustness, because ideally we want this model to be as to give predictions that are as stable as possible, even to like small changes in the input.
Yeah, I think there's a lot of things I could have touched upon kind of within the discussions that we had, actually. Like even within kind of the stratified sample, one similar approach might have been to, rather than sampling fractions of clusters, we might sample clusters themselves. So maybe we train our model on data from certain regions, and then we test on it's never seen bots from a certain region, and now it has to classify those correctly, or it's never seen bots from a certain group and now has to classify those correctly.
Yeah, and that covers like both in some sense in distribution and out of distribution evaluation too, and that's also very important for in general developing very resilient robust models. All right. So I thought that this was a really informative interview. Thank you again for being here. And thank you, everybody watching our videos. And good luck on your upcoming interviews. Bye, everyone.
Thank you. Bye.